Hi folks, and welcome to this programming channel that today will change topic a bit. Usually here we talk about system software. Today we will be talking about neural networks. Why? For starters, neural networks are an old passion of mine. 20 years ago I wrote my first neural network implementation when it was not so cool, and even if focused on other stuff on my programming career, I always continue to play with neural networks. So this is a tribute to two things. One is the modern neural networks architectures, like the transformer, the convolutional neural networks, and so forth. And another is a tribute at the same time to the basic idea of the feed-forward neural network and backpropagation for learning of the weights. Because the new models are giving us incredible results, but the mother of the new and more performing architectures is the feed-forward network. We will do an experiment here for this tribute. A great researcher on the field of machine learning that produces videos that did something very important. They brought many people without a background in an academic background in machine learning into the field. And one of his latest videos, which is extremely cool, is one where in a couple of lines of Python builds a mini transformer with multi-head attention, just with a very simple tokenizing strategy of just splitting characters, but it demonstrates how attention works, how such a neural network will perform even if very small, with just a few millions of parameters. So in this video the idea is to show at the same time two things: how powerful these new models are, these advanced models that use priors, information that we have about data that we are processing and in the way we are processing them, and at the same time how incredible the mother of all the neural networks, which is the foundation of all the advanced models, which is the feed-forward deep neural network, is per se, even if it cannot reach the level of the more advanced setups, it is still unreasonable powerful, given that there are no priors built inside this simple neural network that is the fully connected feed-forward network. So to start, let's focus on what are priors, because we want to understand very well what priors are, because we want in our experiment avoid to all the costs that we introduce priors in our neural network, because we want to see how a neural network that has no clue at all about what it is doing will perform. Convolutional neural networks, priors are extremely obvious. For starters, we know that we are processing a bidimensional array of pixels, so we apply convolutions which are two-dimensional. Also in the max pooling, everywhere there is in the components this idea of two-dimensional vectors, till we flatten finally our vector, and we use a fully connected neural network in order to do something with the features that we extracted. But before this stage, we always are dealing with bidimensional data. Another key thing that priors do in the case of convnets is to understand that if I find a feature in a given location of the image, I can also find it at a different location of the image. So the convolution weights can be shared across different positions of the image. And this is so important because this will allow me to do the same work and even better with a lot less weights. Similarly, in a transformer, the attention weights are shared, and there is this idea inside the way the transformer is built that there is that it is designed in order to process sequences of things. Moreover, in the idea of embedding, there is also this clue that we are representing in different parts of the networks the same set of tokens, and so forth. And we don't want any of that in order to see how a very simple neural network will perform. We want to build a network without any priors built in the network in any way. So the first thing that we want to understand is how the original video did the tokenization. It's very simple. Basically, what we do is here to split the dataset into individual characters. So we will not use any advanced tokenization, and we will have a given number of symbols that we want to represent as inputs, and also that we want to predict as outputs. There is a function that, given a string, will turn it into an array of indexes in our vocabulary, and the function performing exactly the contrary task. And that's it about the tokenization itself. And then we have a function that gets batches of data. Basically, this is random sampling in our dataset, which is this one. So it's works of selected works of Shakespeare and glued together, and it's very, it has always the same format. So basically what we want to do with our neural network is to predict the next character in a given block. So if this is a block of text, I want to predict the next character here, which is likely T. And then what I do is to basically I take the block before, I remove the first character and add it, you know, like in any language model for text generation, I remove the first character of my input in my context and add the prediction, and then I want to predict another character, and so forth. That's the idea. How we do design our neural network so that it has no insights, no priors about the input? Well, this is going to require a very vanilla feed-forward network where the inputs will encode in some way the different input characters. Hello. And then there is a fully connected network with a few hidden layers, and as output I will have my 65 classes, and in the training data, in the batches that I create for training, all the outputs will be set to 0, but there will be a 1 in the actual class of the next character which follows in our dataset. This is called one hot encoding, and this is very used in machine learning, even if it's an incredible wasteful way to encode data. So basically, when I at inference time, when I run my network, what will happen is that the output layer will be all the possible output characters with a different number here, depending on how likely it is for this to be the next character in the sequence. So here I apply softmax to turn the vector into a probabilities vector, and then I perform random sampling weighted by these probabilities, and I can produce the next segments. Of course, I cannot just take the input here with the greatest value, otherwise the network would be deterministic and would likely loop, producing again and again the same text. Let's talk about the representations. So we want our network to get as input the different characters in our block. I use a block of 64 characters. How do I represent the single character here? One way to represent the single character is to use a one-hot encoding. In the one-hot encoding, if for example I have a vocabulary of 4 different characters, I create a vector of 4 inputs where all the are 0 but the one that I want to represent. So for example, if this is character number 2, number 0, number 1 and number 3 of the 4 characters in my vocabulary, this is the representation for character number 2. And if I want to represent character number 3, I will have 3 zeros and 1 here, and the character number 0 is like that. But what this means is that if I have 65 different characters and a block size of 64 input characters, this will be extremely wasteful, because I need 0, 0, 0, 1, 0, 0, 0, 0, 65 inputs for each of my 64 input characters. And so if we do the math here, it's a lot of inputs. So if I want a larger context input, this explodes and becomes huge. Also, there is a very interesting thing to note here. Let's imagine this vocabulary of size 4, and here I have my first input 0, 0, 1, 0. Let's imagine that I have just 3 hidden units here. Okay, so I have all these connections. However, all the weights here will be multiplied by 0. So all the weights departing from this unit will be 0 and will not do anything in the sum here. Only this one, which is 1, will use the weights. So I will actually, my activation will be only driven by this one here. So it will be this weight and this weight and this weight. And if I write this vector here of the weights, I will have, for example, 0.1, 0.5 and 0.3, which are my weights, and these weights will be learned during the training. This is how embeddings were invented. Based on this observation, one could tell basically the one here in the one-hot encoded representation is just selecting a different set of weights, and given that's like that, and given that I know that my inputs are representing the same classes, word after word or character after character, I can just use a lookup table and select the right set of weights. And this is how embeddings started. So embeddings are another case of weight sharing. So this representation, one-hot encoded representation, is too wasteful for our network. It will create a lot of problems during learnings. An alternative to one-hot encoding, which is less wasteful, is binary encoding. So, for example, if my vocabulary size is 4, I will use just 2 inputs. Class 0 will be just 0 in binary. Class 1 will be like that. Class 2 will be like that. And class 3 will be this. Okay, in this way I can use just a lot less logarithm of 2, basically, of the number of items I want to represent. But there is a problem here. You see that there is a very uneven activation of the units. For example, this will not use any weight because they are both 0, and this instead will activate everything. Also, there is the problem that very similar patterns like 1110 and 1111, those will be very similar, even if they could represent completely different things. So there is a bias basically in this representation that can create problem. So I try to come up with something new, which I called permutation encoding. So basically what I do is that if I have a vocabulary size of 4, is to represent each item with different permutations of patterns having the same number of 1 and 0. So that's 1, this is another 1, this is another 1, and this is another 1, and so forth. The number of things I can encode is factorial of n, but I need to because this one can be swapped, and also this can be swapped. So the total number of permutations would include a lot of repeating items of all the ways I can arrange the same ones and the zeros. So I have here half n factorial times all the permutations of the ones in my sequences and all the permutations of the zeros in my sequence. This number here. This reduces a lot the dimension of my input because, for example, if I use just let's do the math. If I use just 12 inputs for each character, for a word or whatever I have, I will need to use 924 inputs with one-hot encoding. That would be terrible. So let's see how this works in our code. Gen coding pattern is the function that I wrote to do that, and we just create the first pattern of zeros and ones. Char encoding length is the number of inputs that we use for every character. Then I generate random permutations of this one and check if they already exist till I have all the permutation that I want. Let's try. Okay, so as you can see, I have 12 tensor of length 12, and each one will have 50% of zeros and 50% of ones in different shapes. Once I do this, what is the setup of my neural network. So I will have a total of 5 linear layers with dropouts as the only normalization technique that I use. And I use a kind of a funnel-shaped neural network. So the input is just the number of characters I have at input, which is my block size, which is 64, times the encoding length, the inputs that I use for each character, and then I have just linear inputs which are progressively smaller. You see the number of hidden nodes starts at 2048, and then it gets reduced with the division here and so forth. So if you want to see the actual layout of this neural network. Okay, this is basically our neural network. Vocabulary size 64, encoding length 12. There are 5 million parameters in this feed-forward network, called simple language model, and you see the inputs is 65 times 12, and it fan out to 2048, which is my first hidden layer dimension, and then the next layers are 2 layers that are smaller but the same size, and then one that is the final part of the funnel, and the output which is even narrow, just my 65 characters. And in order to start the learning of this neural network, I can just start this, the training program. Okay, initially basically the loss is the maximum possible, which is 4 point something, and the model will just output total garbage. Let's see how the training works. Okay, what I did here I modified quite a bit the original mini GPT code. The optimizer used is the same in order to, you know, use very similar things, but I do checkpoints, and every time I found a model which is performing better, so the loss, the validation loss is smaller than the past one, it gets saved on disk. Also, what I do is a training log file where I have my iteration number, the loss in the training set, and the loss in the validation set. So I can monitor my neural network. I can visualize basically the loss of the network. All this code will be found in the repository, which is linked in the description of this video below. So what happens here is that iteration after iteration, the network makes some sense of the data, and for example at some point it discovers that most characters are lowercase and they are separated by spaces, and then it discovers that there are names in uppercase and then colons after these uppercase names and so forth. If we let this network train for quite a bit of time, the result that we obtain is this one. So basically I can execute this neural network if I specify the dataset so that it can rebuild the vocabulary, and then I specify a set of weights checkpoint weights that I saved during my training. As you can see, even this very simple feed-forward neural network discovers that learns words and the structure of the text and so forth. And the final loss will be like 1.65. The GPT model with attention performs much better in just a couple of steps. However, each step takes a lot more time in order to train, but it will reach a lower loss of a network of similar size. So it will get a lower loss of 1. Let me see. The minimum is 1.57 or something like that, and it will perform better, will invent less words, most words will be existing, and so forth. One important thing that we must realize is that if the data set is of this size, I cannot really train a model which is performing very well, because after some time the model will find ways. If it is too large, it will find ways to overtrain, and if I use too much dropouts, it will not perform much better than that anyway. So there is a limit because of the data size that I'm using. So let's see how the full training went when I tested it for a couple of hours. Okay, so if I plot my training curves of the training loss and validation loss, what I see is that compared to transformer that in a few iterations was able to converge much faster, here in order to reach basically the lowest point, which is here 1.3663, it took 500,000 of iterations, even if the iteration is much faster with the feed-forward network compared to the transformer, where there is a huge difference. But still, it is incredible that the feed-forward network is so capable of, learning structure and to learn the names and many words, my data, bot, and professed Q. Okay, it's nonsense to voices to. It's mostly nonsense. Like, but the output is quite interesting, because there is to understand this thing here. So in our network, basically, which there is this permutation of 1 and 0 and so forth, the network doesn't know anything, doesn't know boundaries that are between words. It doesn't know that its goal is to predict the next character. That is a classification task. Nothing is encoded inside the network. So the fact that it works so well is also a really incredible statement of how powerful feed-forward neural networks are. Okay, I hope this was somewhat interesting, and if you want, you can download the code and train it against the Divina Commedia of Dante, and you will see that the performances will be much different using the Divina Commedia. The loss that you can achieve will be lower because the dataset is smaller, so the network can specialize better on the vocabulary which is contained inside, and so forth. Okay, that's all. Bye.